This video is over functions. So let's start with some definitions. The first definition that we have is a set of ordered pairs, x and y, is a relation between x and y. So we've seen ordered pairs last time when we started to graph some things. Now we want to know what's the relationship between those two ordered pairs, and that's exactly what we call them, just a relation. Our next set of definitions are domain and range. So if we have a group of x values and if we have a group of y values, we want to name them something. The group of x values is called the domain, and the group of y values is called the range. So we want to figure out how exactly do these domains and ranges relate to each other. And that leads us to the definition of a function. A function is a relationship between x and y such that for each x value you plug into your relationship, you should only have one y value. So you should not plug in one x value and get more than one y value that relates to it. So now that we know what functions are, let's see how they affect us in our day-to-day math life. So let's go back and let's review. Okay. We want to graph this equation, y equals 3x minus 5. And to graph it, the only way that we know how at this time is to plot some points. So we need to pick some x values, figure out what y values relate to them, and then that gives us our ordered pairs, and so we graph it from there. I'm just going to do a few quick points here so we can get on with the rest of the video. So the first x value that I'm going to pick, let me just suggest we pick x equals 0. So that gives us y is equal to 3 times 0 minus 5. 3 times 0 cancels out, which gives us our y value is equal to negative 5. So that gives us the ordered pair x equals 0 and y equals negative 5. So that is one point that we can plot on my graph. And I've got it plotted down there. Now we need some more points. So let me graph x is equal to 3. And we need to figure out what y value coordinates to that. So we have y is equal to 3 times my x value of 3 minus 5. So y is equal to 9 minus 5, which tells me that y is equal to 4. So that gives us the ordered pair 3 and 4. So plotting that is the right 3 units and up 4 units. Let's go ahead and pick at least one other one. Let me just pick the x value of negative 2. So that gives me the y value of 3 times negative 2 minus 5. So negative 6 minus 5, which gives me negative 11. So that gives me the ordered pair of negative 2 and negative 11. And that ordered pair is way down here, almost off my graph. This is all the points that I need for this example, mostly because I know what this looks like. If you did not know what this graph looks like, then you would probably need to pick some more points to go with it. Okay. This is going to be a line, so all I need to do is graph my line connecting those 3 dots from there. So that is our review example of how we graph some things, just plotting some points. You can double check this by plugging it into your graphing calculator if you would like. What I'm trying to lead you to at this point is the relationship between your x values and your y values, because that was the definition that we talked about. What is a function and how does that function relationship work? Well, mathematicians back in the day did not like the system that you see here on the screen. They did not like saying, well, in one statement, I have my x value is equal to 0. Then in a second statement, that gives me my y value is equal to negative 5. There's nothing relating those two things in one nice mathematical statement. They're in two separate places on our screen. So what they did was they invented a notation to relate these two statements. So instead of using y, they're going to use f of x instead. And it looks like f times x, but the way that we say it is f of x. So in our examples, they can be written as y equals our mathematical statement, or if we're trying to graph things and in other places, we might also see this function notation. F of x is equal to our statement. And let's see the advantage of taking out y and putting in f of x. Let me work out the same 3 points that I worked out last time. The first one that I substituted in was x equals 0. Okay. The way that this works out is we're just going to plug in 0 into every time we see an x in our expression. So we have f of 0 is equal to 3 times 0 minus 5. And that simplifies to be negative 5. So we have this in one nice expression. We have our x value is 0 and our y value is negative 5. So now we have one statement that connects our x and our y values. That means it relates our x and our y values. So if we were trying to come up with an ordered pair and a graph from this, we could very easily see that gives us that point of 0 and negative 5 in one statement. So if I did it again with my last point that I used, f of negative 2, I again just substitute in negative 2 for any time I see an x. So f of negative 2 is equal to 3 times negative 2 minus 5, which gives me negative 6 minus 5, which gives me negative 11. So I have, again, one statement that connects my x value of negative 2 and my y value of negative 11. Now, if our goal was to graph this, then we would go ahead and write this as an ordered pair or a point. If your example does not say anything about graphing, then this statement here is your final answer. Now, the question is why did they use f of x? And the reason that they used f was to go along with the word function. So function starts with f, so that's why most of our functions will be represented by the letter f. But f is not the only letter that we see. Most of the time they went with the alphabet, so we can see f of x, or g of x, or h of x is notations that we see quite often, or they can use the capital letters, so capital F of x, capital G of x, or capital H of x. Those are also function names that we see quite often. And what they are is exactly what I just said. They are names. They're a way to label each individual function. Now, these are the standard ones that we use, but if we were talking about an applied problem, then we might use a variable to represent the specific applied problem. So if we were talking about a cost as a function, then it might be a C of something. If we were talking about cost as a variable over time, then our expression might look like C of t, and that represents our total cost as time changes. Another example of this might be a geometry type of problem. So if I wanted to look at the area of a rectangular region, then my function might be labeled as a capital A for area, and this area might be as a variable over the width or over the length of your rectangular region. So you might see it as area as a function of W, or you might see it as area as a function of the length. So those are some other examples of function notation. Alright, so what we want to do, given this function notation, is we just want to simplify some things now. Again, if our ultimate goal was to graph it, then we would change it into ordered pair form, but this problem does not say anything about graphing it, so we just leave it in the function notation. So in part A, I want to figure out what g of 2 is, given my equation or my function notation up there. G of x is equal to 2x squared plus 1. So all we do is we take this 2 and we plug it in for every place that we see an x. So G of 2 is equal to 2 times 2 squared plus 1. And then we just use our PEMDAS from here. So first thing is exponents. So 2 squared simplifies to give me 4. Then we do multiplication. 2 times 4 gives me 8. And last, we work our addition. 8 plus 1 gives me 9. So my final function answer here is G of 2 is equal to 9. Go ahead and pause the video and see if you can figure out how B works on your own. See if you can figure out what G of negative 3 is. Again, we just substitute in negative 3 for every place that we see an x. So we have G of negative 3 is equal to 2 times negative 3 squared plus 1. So exponents first. Negative 3 squared gives you positive 9. Positive 9 times 2 gives you 18. And 18 plus 1 gives you 19. So the answer to this problem is G of negative 3 is equal to 19. I have a couple more examples of this here. Given the exact same function, G of x is equal to 2x squared plus 1. But this time, we don't want to figure out what G of numbers are. We want to substitute in variables or letters. So, pause the video and see if you can figure out how part C works. What is G of A going to be? So all we do again is we substitute in A every time we see our variable in the original problem. So that gives us G of A is equal to 2 times A squared plus 1. And that's pretty much all we have to do on this function here. Since we cannot simplify, then we cannot work anything out farther. The only thing I can do is remove those parentheses. So my final answer here is G of A equals 2A squared plus 1. So basically all we did in part C was we took out the x's and we put in the a's. We really just changed out the variable. The reason that we did part C is to help us with part D. How is it going to work when we're trying to figure out what G of x plus h is? Again, one more time, you just take this x plus h and you just substitute that in for any time you see an x in your original expression. So, pause the video and see if you can figure out that one on your own. Okay, so we have G of x plus h is equal to 2 times, substitute that in, x plus h squared plus 1. So we took out the x's and we substituted in an x plus h. To simplify this, we need to figure out what x plus h squared is. Remember, you cannot distribute that square when your operation is addition or subtraction. So the way that we need to do this is we need to FOIL what our x plus h is. So first, x times x gives me x squared. Outside, I have an x times h. Inside, I have an x times h. So if I wanted to combine these together, that would give me 2 x times h's. And last, I have h times h to give me h squared. And that is plus 1. Then we need to distribute our 2. So that gives me 2x squared plus 2 times 2 gives me 4xh plus 2 times h squared gives me 2h squared plus 1. Now none of those are like terms, so So we actually cannot simplify any farther. So our final answer to this problem is g of x plus h equals that whole mess on the right, which is 2x squared plus 4xh plus 2h squared plus 1. So now that we know what function notation looks like, and we know how to simplify it along the way. By the way, I just wanted to let you know that part D, that was the first step to a calculus problem. So if you need to take calculus in your future, then you are one step ahead of the game.